We're going to be doing a couple things that are maybe slightly unusual in this course, and I'll just let you know right now. So you'll notice that we're being filmed right now. So what we're going to do is post all of the lectures online. And so you'll have video recordings of all the lectures. That'll go through iTunes U, and it will go through the Online Learning Center at UCI. And I'll send you out links, et cetera, to those when those videos become live. So usually within a couple days of me giving the lecture, those lectures will be posted in various formats online that you can then watch later. And I'll talk a bit more about that once we get going with everything. So there, let me just make sure. Any questions about logistical stuff? You're in the right room? Okay. So this course is Introduction to Cosmology. And I like starting off this course with a picture like this. What are we looking at? This is an ancient Mayan pyramid that was built sometime around 1000 AD. So something like more than 1,000 years ago. And this is a great image because it's taken at night. And up here you can see the constellation of Orion rising up over the back of this pyramid, coming in through some clouds. And you can imagine the people who built this pyramid and who spent time around this pyramid 1,000 years ago looking up at a night sky that was not very much different than this. And in fact, we think that those people understood a lot about what was going on with the sky at night, because the actual architecture of this pyramid and how it's laid out tells us that. So one of the really cool things about this pyramid is if you go there on the night of the equinox, so around the time the sun is setting in that special time of year, in fact it happens twice a year, when day and night are roughly the same length. So it's a special day called the spring, for example, the spring equinox. And you look at the shadow cast by these specific bricks along the side of this pyramid. It looks like there's some kind of snake crawling down the side of the pyramid. So it plays in the shadows and the lights just at that time of year and makes it look like a snake is crawling down the edge of the pyramid. And just at the edge of the pyramid where that snake kind of comes down, there's a snake head that's built into the pyramid. So it's pretty obvious that these people, these ancient Mayans, understood the cycles of sunset and sunrise. They knew how the sun changed in the sky over the course of a year, and that was important to them. Their cosmology was cemented in what the night sky was doing. So what cosmology is, it's really the subject where we try to ground ourselves and ask ourselves questions about the broad principles that govern the universe, what the universe is like on the largest scales. And so it's those kind of big picture questions that people have asked themselves for thousands of years when they look up at the sky at night. That's what we're doing in scientific cosmology today, and at some level that's what this course is about. So the big questions we're going to tackle in this course are, and many of them are related to, you could imagine, the very same questions those ancient people were asking themselves when they looked up at the sky and they saw Orion rise up over this pyramid. So how old is the universe? How long have we been here? Is it infinitely old? Is it cyclic? Do things happen and then re-happen again? Or is there some finite beginning and there's actually an age to the universe? How did we get here, if so? So how did we end up looking up at the sky at this stuff? How far away are those stars? And what are those stars? What are those lights up there in the sky that appear to circle us every day? More generally, how big is the universe? If we can measure it, how far out does it go? And then specifically in this course, because we're in the era of modern cosmology, we know of some really exotic things that exist out there. For example, black holes. They're a really extreme phenomenon that until maybe less than 50 years ago, people thought didn't actually exist and were just a mathematical construct. Now we have a fair amount of evidence that these things really do exist. They're extremely powerful. And what are they? What is this thing that you may have heard about called the Big Bang? That in modern cosmology tells us this was the beginning of all space and time. What is it? Why do we think it happened? And what does it mean for the evolution of the universe after that beginning state. So these and many other questions are the kinds of things we're going to try to tackle in this course. And in the context of this, very importantly, underlying it all, is we want to know the answer, how do we know this? So rather than this being a course where I'm just going to tell you things, I will tell you things and talk about cool stuff that we know, underlying all of this is that we know all of this stuff for a reason. Okay, we've spent a lot of time and energy. If you think about it, the course of more or less all of human history has been an effort to try to look up in the sky and figure out what it means. So there have been a lot of people thinking really hard for a very long time and now applying the full power of the scientific method to this question. So how is it that we're able to figure out the answers to these questions, and what is the limit of our current knowledge? So that's the context of what we're doing in this course. Are there any questions? Okay. So before I go on and give the first lecture, I just want to sort of give some overview about what we're going to be doing this course, how we're going to be doing assignments and grading. So basically, your grade is going to be based on two big chunks. So the first is a couple of exams that add up to 46% of your grade. And they're both basically midterms. There's not a final. There are basically two midterms. They're both going to be given in class, in this classroom. The first is on Friday, February 2nd, and the last one is on Friday, the 13th of March, unfortunately for you. But I don't believe in superstition, so the 13th of March it is. The aim here is just to encourage you to follow along with the material, pay attention to lecture, ensure that you're paying attention to the big concepts. So that's the point of these exams. And then a slightly larger chunk of your grade is going to be based on sort of more in-depth projects. So there's going to be two homework assignments that I'll distribute. They're each worth 10% of your grade. There's a final paper, and the final paper I'll talk a bit about later. But the final paper will be due on the Monday of exam week. And I'll give you about a month lead time before I talk about what I want specifically in that paper and when it's due. But basically, this paper is going to be either an in-depth discussion of something that's going on in the popular science literature, like on scientificamerican.com, or that you might find on Google News, of something in cosmology that's happening basically now. And then you can do a little in-depth research on this thing and write a paper on that. Or if you prefer, you can do what I'm going to call a scientific biography on a key figure. And I'll be talking about a lot of key figures in the history of cosmology in this course. And you can pick one of those figures or pick somebody else who you're interested in and do a paper on that. And the context of this is, I just want you to find something that you think is interesting, and then spend time on it. That's this. So it's a pretty open-ended assignment. And really what I want to do is give you an excuse and a reason to spend time on something you think is cool and interesting and dig into it and write a paper on it. Finally, there are some online modules that I'm going to discuss in more detail on Wednesday. But it's through a website called RocketMix. And through RocketMix, you can do online learning modules in various courses. And in this course, there are about 4 of them that throughout the course of the quarter, I'm going to have you do. And they'll take 15 to 20 minutes to go through. And they're sort of these interactive learning exercises that will teach you about different concepts that I think are important in cosmology. So the class website is going to be your main resource. I imagine this is pretty common in your courses today. On the class website, you'll find the schedule, what we're doing, when things are due, when things are assigned. There'll be PDF files of all the lectures, like the slides from this lecture will be up. In fact, they're up now. Once these videos are processed, I'll do links to those videos, the video lectures, etc. As I mentioned, all of these are going to be recorded and podcast, so you can go to iTunes U or ocw.uci.edu to look for this class as posted. There'll be YouTube, basically, videos there. And then, of course, the class website. And then finally, rocketmix.com, which I'll talk about now. So if you haven't looked at the website already, this is what it looks like. And it's pretty obvious, but I'll just sort of go through it. You can go to the home page, which is here, which is sort of overall stuff. I will link the assignments here as PDF files. And then when they're released, I'll send you an email reminder about it. I'll post the solution sets right here on the main page. The syllabus is posted there. I'm going to assume that you've all read it. Okay, if you haven't read it yet, please read it. I'm not going to go through every line of it, but you're responsible for knowing what's on the syllabus. This is where you'll find the lectures. So this is where the PDF files of the lectures are, et cetera, right here on the lectures page. And then finally, a more detailed schedule is on the scheduled page. And here I'm going to clarify when discussions are canceled. Most of them are canceled. When the rocket mix modules are assigned, and et cetera. And then just for ease of use, right here is a calendar. And everything in cyan here, these bluish numbers, are when things are due. And the magenta dates are when class is canceled, right? So this is MLK Day right here, and I just to remind you, no class on that day. Any questions about logistics stuff like this? Okay. The textbook for this course is optional, but some people like to have a textbook, and this is one that I like. It's called 21st Century Astronomy by Hester et al. What is not optional are these online modules that you'll learn more about next time. Eventually you can sign up for this course through rocketmix.com. The cost is $20. I've talked to the people who work on RocketMix. This seems to me like a fair price, especially since you're not required to get a textbook. It's actually cheaper than most textbooks. So hopefully that won't be too problematic for you. But what you'll do is you'll go online, give them a credit card number, and then they'll give you access to the site. I mean, it's safe. It's not like it's crooks, you know. Just email me your credit card number, and everything will be. Okay. So are there any questions before I begin this lecture? Okay. So for this lecture, all this is an introduction. So my goal here is to provide an introduction to cosmology, giving you kind of a broad brush picture of what we know, and then we'll back up in the next lecture and sort of start to progress towards how we began to understand these things. This is an image taken out at Joshua Tree, not too far from here. And so one of the things that we often forget is how amazing the night sky can be when there are no lights, artificial lights, glaring your view. But the ancient people who were living thousands and thousands of years ago saw this regularly, right? There was no TV, there were no lights in their face. At night, if they looked up and it was clear, they could see amazing things. And one of the things that they noticed was there was a tremendous amount of regularity. Unlike the sort of world you're trying to survive in down here on Earth, right, where chaotic things can happen, the things in the heavens seem to organize themselves in periodic ways. So every night, the sun would go down, and suddenly you could see the stars because the sun wasn't blocking out their light. And these stars would rotate overhead in lockstep. And they would stay locked in configurations as they rose up and then set. And some of these configurations were so compelling that people associated them with pictures. So these are constellations, right? That looks like a bear, or that looks like an archer, or whatever. And they would see these pictures in the night sky rise up and then set. And in certain times of year, they could slowly reveal new constellations that you couldn't see before. And because sometimes you would see these constellations, and then sometime later, suddenly the hunting would get good, or suddenly berries would bloom, they began to notice that there was a correlation between seeing things up in the night sky and things that were happening here down on Earth. And so it's not necessarily crazy that some people then began to say, hey, because there's a correlation here, maybe there's causation. Maybe it's because those lights are up there in the sky. Maybe that's making the game particularly good this time of year. Right? Maybe that's making the berries bloom. And so this idea of astrology came about because of these sort of natural correlations that people saw. Of course, today we understand that that's just because things are correlated doesn't mean they're causing each other. Right? The reason why things begin to bloom in the spring is because it's getting warmer. The reason why it's getting warmer is that the Earth is tilted, and in that time of year, the part of the hemisphere where it's becoming summer is beginning to tilt more towards the sun, and things are warming up. But now, because the Earth is tilted in a different direction than it was before, at night we can see new constellations that we couldn't see otherwise. So it took us a very long time to figure this out. On some level, it was sort of tricky. The universe played a trick on us to make it seem like it was correlation, to make it seem like it was causation, when really it was just correlation. So the task that people had, living thousands of years ago, was a difficult one. This is an image of the night sky at dawn, actually, taken in Central Africa. I find this image really compelling because you could imagine the first modern humans to walk the Earth. Okay, so this would have been something like 100,000 years ago. Would have stood and seen a night sky that was not very much different than this. Now, the one thing that would have been different is this is a distant town. So that wouldn't have been there. We'll cover that up. But otherwise, people living 100,000 years ago, who, as far as we could tell, were just as smart as us, would have looked up at the night sky and seen something like this. It's hard to imagine that those people would not have been asking themselves the same questions we ask ourselves at night when we look up at the sky. What is this? How did we get here? What are these bright things? Now, it's an amazingly beautiful picture, but it's also extremely deceptive. Because your eye is drawn to the bright things. Okay? In addition to the sun, there are these bright planets, Venus and Jupiter. They're so bright, they seem really important. They must signify something important about the universe we live in, the fact that these things are there. They're different, by the way, than the stars, because they move with respect to the stars. The word planet means wanderer. They wander with respect to the background stars, and that's a clue that they're different somehow than the stars. They're also brighter. It's extremely deceptive because a bright star like this outweighs Jupiter like a watermelon does a lime. And it's a testament to how far away that star is that we can easily confuse it. Because what it is another sun. It's actually something that's as bright as the sun. It's just so far away that it's dimmer than even Jupiter. And Jupiter isn't even shining. Jupiter is just reflecting the light of our own sun. So this picture that they had to deal with, this information they could see, was a very difficult puzzle to try to unlock. And people have been trying to unlock it for thousands of years. Now let's flash forward way in the future to 350 BC. If a Greek philosopher was looking up at this image, right, was looking at the night sky, let's say it was Aristotle, he would look at this and he would say, I got it. I know exactly what's going on. I figured it out. The Earth that we're standing on is, of course, fixed. It's not moving. And all of those stars are rotating around us every 24 hours. They're just circling around us. The planets are also circling around us, but they're circling at a different rate. They live on a different sphere, and they circle at a slightly different rate, and that's why they wander around with respect to the background stars. This thing right here, it turns out, is the Milky Way galaxy. I'll talk a bit about what that is in a second. But it turns out that every single star that you can see by eye at night is actually embedded in the Milky Way galaxy. The Milky Way galaxy is a vast disk of stars. It contains more than 100 billion stars. It's so large that if you shrunk it down to the size of the Pacific Ocean, our entire solar system, you can throw in Pluto if you want, our entire solar system would be the size of a maple leaf floating on the ocean. Now imagine a bee who's landed on that leaf. A piece of pollen on the leg of the bee, that's the sun. And the Earth is microscopic on that scale. The nearest star to the sun is a half a mile away. You can forgive the ancient Greeks for not having it all figured out, floating on that leaf, right? Trying to make sense of this ocean that they're embedded within. But it was certainly true that Aristotle did not know what was going on with that. He thought, in fact, that it was a feature in the Earth's atmosphere. That it was an atmospheric thing, that that part of the atmosphere was burned in a rut or something. And that it had really nothing to do with cosmology or the universe at large. It was within the orbit of the moon. Let's flash forward another 1,300 years or so, almost 2,000 years, to Isaac Newton, the European Enlightenment. By this time, people had figured quite a bit out, right? The Earth said, no, no, no. Or Newton said, no, no, no. The Earth isn't locked down. It isn't immovable. In fact, it's moving and it's spinning. And the reason why it looks like everything goes above and down every 24 hours is we're actually sitting on something that's spinning on an axis. Those stars are distant suns, and therefore they're really, really, really far away. So Newton had a sense of just how big the universe was because these stars are so far away that they're dimmer than the planets, even though they're as bright as the sun. But even Isaac Newton, who was a pretty smart person, didn't know what was up with the Milky Way galaxy. He didn't know really what it was. He didn't understand that what it really was just our galaxy. And that there are, in fact, many, many other galaxies out there in the universe. When Newton closed his eyes and thought about what the universe was on the largest scales, he thought of something like this. An endless sea of stars. Each of those stars is sort of like the sun. And in fact, it was sort of a depressing universe if you think about it, because just star after star, it just kind of went on forever, and that was it. And in fact, I think that there are a lot of people today, if you ask them what the universe is, they think, it's something like this. It's sort of star after star, and there's a lot of them, and they're sort of like the sun, and it kind of makes me depressed. I don't want to think about it anymore. But this is, in fact, not at all what the universe is like. So Isaac Newton, despite being a super genius and all, was wrong. We know now that this is not the universe. This is not a good picture of what the universe is like on the largest scales. Our universe is a universe of galaxies. Each of those galaxies is like that ocean of a Milky Way, containing more than 100 billion stars. And in fact, we think that the entire universe that we can see contains more than 100 billion galaxies like our Milky Way. This picture here shows a local map. 10 to the minus 8th of the visible universe is shown in this picture here, where every single dot represents a galaxy, each containing 100 billion stars. So the universe we live in, at some level, if you could characterize it in one way, it's that it's a universe of galaxies. And that from all the time that the universe has existed since the Big Bang, what the universe has been doing is making galaxies. And those galaxies make stars, and around those stars form planets. Another thing that stars do, and the reason that stars shine fundamentally, is they are fusing new atoms. Those stars in these galaxies are making new atoms that have never existed before. In fact, we think the universe was born of material that was extremely simple. just hydrogen and helium. And the only reason why we have anything that's more complicated than hydrogen and helium, right, so that includes oxygen, carbon, iron, is because those elements were crafted in stars after the Big Bang. The first stars formed and died. After they died, they blew these elements out into their constituent galaxies, and the galaxies scooped them up again to create a generation of planets. And it's rocky planets like the Earth that have made good use of those heavy elements. Virtually all of the key elements for life were generated in stars after the Big Bang. So what are some other things that Isaac Newton didn't know? So according to modern scientific cosmology, and again, I'll walk you through the evidence for this later, all of space and time, so not just time but also space, was created about 14 billion years ago in something that we call the Big Bang. So in the context of this picture, it actually doesn't make sense to ask what was going on before the Big Bang because time started then too. Now, that's a very specific model of what the Big Bang is, and I'll talk about alternatives to that towards the end of this course. But that's one specific model of the Big Bang. It was born hot and small, and it's been expanding since that time. In fact, it was so hot in the beginning that only elementary particles could exist. So one way to think about that is, imagine you take a big container and you just squeeze it and make it smaller. If you don't let anything out as you squeeze it and make it smaller, what happens to the molecules in that container is they start bouncing off the container faster. And the speed with which molecules are bouncing around is basically the temperature. So if you took something and you squeeze it down, basically what happens is it gets hotter. So because the Big Bang was born so dense, it was born extremely hot. And in fact, it was so hot that nothing complex could exist in the beginning. So another way to think about that is, imagine you're in this room and we start cranking up the heat. Everybody leaves because it's going to get really hot. We keep cranking up the heat. It gets so hot that the seats start to melt. And we keep cranking up the heat. It starts getting so hot that even the liquid can't stay liquid and begins to evaporate. So suddenly we have this gas. And the gas contains nothing but the molecules that at one point in time made up these seats and everything else that's kind of interesting in the room. So it becomes so hot that nothing kind of interesting or complex like a seat or a desk or any of this equipment could exist. But you still have these molecules, these kind of complex molecules. But if you keep cranking up the heat, the molecules bang into each other and break apart into their constituent atoms. So now you don't even have molecules anymore, you just have atoms. If you keep cranking up the heat, even the atoms start to break apart. The neutrons and protons that are bound together in the nuclei of those atoms bang into each other and break the nuclei apart. And now you have a sea of nothing but neutrons and protons and the electrons that at one time orbited those atoms. And that's it. So you start off with something as complex as this room, made of all kinds of different stuff with lots of different colors and complex things. If you make it hot enough, it becomes very simple. You just have neutrons, protons, and electrons. And that's it. So in the very beginning, right after the Big Bang, it was so hot that nothing complex could exist. By necessity, it was basically born with just neutrons and protons. Now, if you go back before that time, the constituent particles that make up neutrons and protons were around too. So at some level, the very beginning of the universe started off as sort of the ultimate primordial soup, because it really was just the very basic building blocks that eventually gave rise to everything complex. And over time, The universe eventually built galaxies. The galaxies fundamentally grew because of gravity. We'll talk more about that later. And within these galaxies, stars formed. And after those first stars formed and blew up and created heavy elements, the next generation of stars had planets forming around them. And on at least one of these planets, people emerged and looked back up at the sky and began trying to figure out this whole process. Are there questions? Okay. It's very quiet in here. Like, I feel it's... All right. We'll have to figure out a way to get people talking later. Another thing we'll learn about in this course is that there's much more out there than meets the eye. That not only is the universe really, really big, and it's also, as you'll find out, really, really old, it's made of some weird stuff. We now believe that only 5% of the universe is made of stuff that is anything like what we have experience with here on Earth, anything in the periodic table. Only 5%. 25% of the universe is made of something called dark matter. Now, this dark matter is made of stuff that's we think it's just normal particles, but those particles do not interact strongly with the normal stuff. They only tug on the normal stuff via gravity. And that's going to be a whole lecture. And there's some even weirder stuff that's called dark energy. And what dark energy is, it's a constituent of the universe that's basically driving the universe to accelerate in its expansion. It's as if the vacuum of space has an energy, and that energy is driving the universe to expand at a huge rate. But we'll talk more about that stuff later. So I mentioned this before. The universe is 14 billion years old. That's really old. Now, it used to be, I would say, a number like 14 billion in a class like this, and people would be like, wow, that's really old. But now, you know, with the debt being like 20 trillion or whatever it is, 14 billion doesn't seem so big, right? Like, $14 billion, a lot of people have $14 billion. There's like 20 billionaires who have that much money. But 14 billion years is a long time, okay? So just to put it in perspective, this is sort of a timeline that I've tried to make here in billions of years. We think the Earth formed about 5 billion years ago. The Earth and the Sun both formed about 5 billion years ago. So that is, the universe itself is almost 3 times older than the Earth. So the Earth is sort of relatively young. But, you know, the first dinosaurs didn't exist until something like 150 million years ago. That's a tiny sliver of time compared to 14 billion. So you think of dinosaurs as being really old? Not really. All of semi-modern human, anything you would call Homo, in the last 2 million years. This tiny sliver. All of written history is in this tiny, tiny little bit, this green bar right here. Another way of thinking about this is, imagine you took the 14 billion year history of the universe and scrunched it down into a year. And you tried to think of relative times. If you did that, then all of recorded human history would have happened in the last 13 seconds. Shakespeare would have been alive and writing his plays 1 second ago. Like that. So in that sort of time frame, we're extremely, extremely young. And the universe has been around a very, very long time. Are there questions about that? There's one more concept I just want to introduce now that will be important later in the course. And it sort of has to do with time, but it has to do with the finite speed of things. when you're talking about something that takes 14 billion years to happen, that's a very long time. It's very non-intuitive. We're not used to dealing with things that take that long to occur. Also, the universe is really, really big. I've talked about this before, how big the galaxy is. So the thing we're used to getting information from, and the thing, in fact, astronomers get most of their information about the universe from, is light. Now, light, in our everyday experience, travels instantaneously, right? You know, I turn this laser, I press the button on the laser pointer, and suddenly something appears semi-instantaneously on the wall. Right, boom. But really, the light from this laser pointer is traveling at a finite speed until it hits the screen. It's traveling at about 300,000 kilometers a second, which is the same as 186,000 miles per second. Something traveling that fast can go around the Earth almost 8 times in a single second. So the time, you know, the everyday experience we have, light is effectively infinitely fast. But when we're dealing with things on an astronomical time scale, it's not. And it's important that it's not. And in fact, we use the fact that light travels at a finite speed to learn something. So let me give you an example. One way to think about light is it's like a messenger. Okay? You can think of someone on horseback carrying a message. Right? There's a battle that happens. Okay? You've just lost the battle. You need to go tell the king that you've just lost the battle and people need to evacuate the city or whatever. So you go trampling in your horse, and 2 days later you get the news. Oh, uh-oh, you know, an army's coming our way. You can think of light like that, right? Just a really fast horse. So here's the sun. It takes light about 8 minutes to get to us from the sun. Now, what that means is when you look up at the sky and you see the sun, you're seeing it as it was 8 minutes ago. You're not seeing it as it is now. You see the moon as it was about a second ago, because the moon is a lot closer than the sun. So let's go back to this picture and get a sense of that. Imagine you're out, dawn, Central Africa. We're looking at this image. And now suddenly, someone magical comes along, God comes along and throws a switch. Turns all the lights in the universe out. Boom. God is omnipotent. All lights go out instantaneously. Okay. And then we stand here. Then God turns everything back on. Turns the switch on. What happens? Well, it stays dark. It stays dark for about 8 minutes. Suddenly, we see the sun. That's all we see. About 10 minutes later, the sun's light has hit Venus, bounced off Venus, and come back to the Earth. Ah, there's Venus. Then we wait. Depending on exactly where Jupiter is in its orbit, about an hour later, there's Jupiter. That's it, nothing else. No stars. That's all we see. Because light had to go all the way to Jupiter, bounce off Jupiter, come back to us. It takes about an hour. 25 years later, we see that star. Really far away. The thing turned on, you had to wait 25 years. Ah, there it is. Then over thousands of years, suddenly, or not suddenly, gradually, the Milky Way would fade into view. Because the light from all of those stars that make up the Milky Way would eventually start making it to us. So that's it, right? Well, if we had really good eyes and we waited a really, really, really long time, 2.5 million years later, a little smudge would appear up here in the sky. And in fact, you can see that smudge by eye. That's the Andromeda galaxy. That's another galaxy outside the Milky Way. That's so far away, it takes 2.5 million years for the light to get to us from Andromeda. And that's a real picture of it. This is the only galaxy that you can see by eye in the northern hemisphere. Everything else you see at night by eye is part of our galaxy, or at least not another galaxy. So what this means is, as you're looking at things that are farther and farther away, you're looking back in time. So while it takes light 100,000 years to cross the Milky Way, that's small compared to the universe. The nearest big galaxy to us, Andromeda, I just showed it to you, is it takes light 2.5 million years to get to us. So this picture of Andromeda right here is what Andromeda looked like 2.5 million years ago. Before there were humans to look up, this is what Andromeda looked like. Now, it turns out that 2.5 million years is really not that long of a time compared to 14 billion years. But we can look at things that are much, much farther away than Andromeda. And when we do, we see that the universe looked different in the far past than it looks now. So you can use the fact that light travels at a finite speed to basically build a movie of what was going on in the universe a long time ago, and then closer to now, and closer to now. Now, so another thing you'll hear a lot about in astronomy is something called light years. What's a light year? Someone tell me what a light year is. Yes? Yes, exactly. So it's the distance that light travels in a year. Note that it's a distance. Okay, a lot of people, you'll hear the word light year used as a time sometimes. It's not. It's a distance. Very good. Okay. It's in fact almost 10 trillion kilometers. So in a year, a light ray can travel about 10 trillion kilometers, and so we use light years as a unit of measurement in astronomy. That's a natural unit of measurement because the distances are so large. Now, it wouldn't make sense to say, how tall are you? Well, I'm 10 to the minus 8 light years tall. Actually, that would be really tall. I'm 10 to the minus 15 light years tall. No, you wouldn't say that. You would use kilometers or you'd use meters. But for distances in astronomy, a light year makes sense. And so the nearest bright star, for example, is about 8 light years away. The nearest star period is about 4 light years away. The Andromeda galaxy is 2.5 million light years away. So you immediately get a sense of how far things are away by just giving their distances in light years. And so this concept of finite light travel allows us, like I said, to build almost build a movie of what things were like before and what things are like now. For example, this is an image of a galaxy taken with the Hubble Space Telescope. The light from this galaxy left it 12 billion years ago. So we're seeing this galaxy as it existed 12 billion years ago. That's way before the Earth existed. And when we look at galaxies that are this far away, what we find is that they look a lot different than galaxies that are nearby. So what we see is that there's some evolution in how galaxies change over time. They look different at early times than they do now. They are more messed up at early times. They're kind of in shambles. See how this thing is not very ordered? And as you then look at galaxies that get closer and closer to us, they're more ordered. So what you see is a progression over time that galaxies started off kind of messy and small, and they get more ordered and big and beautiful as you approach today. We'll learn more about that, but this is sort of a trick that astronomers and cosmologists use to sort of formulate, to build these pictures of how things change over time. This is a very deep image of the universe. So I wanted to close, I'm going to close with this movie. This movie is really cool. This was made by the Museum of Natural History, the American Museum of Natural History. And what it is, it's a movie that kind of zooms out from the Earth. It started out with the Himalayas. And you'll see it zoom out and begin to sort of show you what we see around the Earth. All of this was made by accurate data. This is real. So You're now beginning to see the curvature of the Earth. Okay, I've got some things I'm going to talk about. We're not done yet. So, you see this, I want to draw your eye to a couple things. Does anyone see this thing here? This group of stars? Does anyone know what this group of stars is called? Yeah. Close. It's another popular one. Yeah? Orion. Right, exactly. Good. So if tonight, you go outside tonight, or any sort of night this winter, and it's clear, you'll see Orion. It'll be over there in the sky. You'll see it. It's like, I'm not very good at constellations, and even I can recognize it. If you try to find it, you'll see it. So this is Orion the Hunter, and you see it over here. Now what's going on? You see there's a shadow right here. Here's the Earth. There's a shadow. Why is there a shadow there and we can see this part? What's going on? Yeah. Yes? Light from the sun, right. So the sun is sort of where the camera is, shining on the Earth. It's daytime in Tibet. And over on the other side of the Earth, where we are, it's dark. Right? See how it's getting dark over there? Okay, so the sun is here, it's daytime here, and people living on this side of the Earth can see Orion at night. See what I mean? Okay. These are all the man-made satellites, what their paths are. See how close they are to the Earth? It'll look really close later. Most of them, they're really circling right around the Earth. Most of them are there to monitor the Earth. There, the camera's circled around, and now we're looking at the sun and the dark side of the Earth, nighttime. That's the moon's orbit. The moon is way out there. And it says at the bottom what the light travel time is. It takes light a second to get there. These are the orbits of the planets. Now what's happened is in this movie, they've dimmed out the sun. They've made it look very dim compared to the planets. But in reality, oh wait, by the way, these are sort of popular constellations. Now they're going to turn the sun on as bright as it would be from this distance. What that means is that it'd be really, really hard to see the Earth if you were just far away studying our star. And now you see all these other stars out there. We think almost all of them have planets. And it's only recently we've been able to detect that. That little sphere right there, let me pause it real fast. That's the distance, the farthest distance that any radio signal Earthlings have ever sent out is over the size of the galaxy. So if there were aliens out there looking for our radio signals, if they were here, they would never have seen them yet. That's 70 light years, that bubble. We're going to zoom out of our galaxy. Remember, our galaxy is small on the scheme of things. So there's our galaxy. We're zooming out. That's 100,000 light years. Every other dot now is another galaxy. Something that's not realistic about this movie is they just put them in as dots, but really every single one of them as complicated and rich as the Milky Way itself. Now, what you see, and I'll explain this later, is that these are all the galaxies we've mapped. It doesn't mean there aren't more. These are ones we've actually mapped. We know where they are. And this big slice right here that we haven't mapped, that's basically the plane of our galaxy, so we can't look there. But all of this stuff is stuff that we've mapped. And then this green ball is radiation that's left over from the Big Bang that we've detected and also mapped. The size of this sphere is about 14 billion light years. At least that's the light travel time. There could be a universe beyond that sphere, but we could never have seen it because the universe isn't old enough. And now it's just going to zoom back in. So the course of this course, I'm going to be talking about how we know this stuff, and I'll be going into more detail on all of these things. All right, thank you.